We've been talking about sequences, and the following is a very popular example, an instructive one, because there are many different points of view that all lead to this one example. What we have here is an infinite sequence that is defined recursively, but more specifically than that, the recursion is defined simply by repeated application of a fixed function f, which is a very simple rational function. So each term is f of the previous term. That means that the nth term is expressed as the nth iterate applied to the starting point, or actually the n minus first iterate applied to the starting point of the sequence. And in this particular example, we'll show that the sequence converges to square root of 2. I said that iterating a function gives a rather special form of a recursively defined sequence, and I would encourage you to think about that kind of recursion in this really graphical way. And once again, although our dynamics all takes place inside the one-dimensional real line, it does help to think about a domain more generally. In this picture, I'm suggesting a two-dimensional domain, but the dimension is not what's important for us. Just think of f as mapping points to points in some domain, rather like the current of a river or wind in the air moving particles along. If we pick a point x naught in this domain, that's the first term in our sequence, then in a single time step it gets moved by the current to a point x1, which then gets mapped to a point x2, the next time step, and from there to the point x3 at the third time step, and so on, thereby generating a sequence of points in our domain, like the individual time frames of a video. If we keep track of the continuous path of a particle like this, it will be also a kind of dynamical system. But because we're iterating the function at integer time steps rather than a continuous time, the dynamical system is really just a sequence defined by iterating a function f. Our goal in this video is to show that the sequence defined by this iteration converges to square root of 2. And for the main part of our argument, we'll need this lemma, which I'll prove now. So suppose x is bigger than square root of 2, then x minus f of x simplifies as shown, giving an expression that's positive according to our assumption, which in fact is the first inequality that I'm claiming in my lemma. And for the second inequality that is claimed in the lemma, what we're trying to prove, first of all, notice clearly that f of x is positive. And now we want to look at this difference of squares, where the right-hand side can be expressed as this perfect square, which is positive. By the way, all the algebra that we're doing here is elementary. You can check it. It's just college algebra. Now, look at the first two factors on the far left. The first of those factors, f of x plus square root of 2, is positive. And by comparing with the right-hand side, that means that the second factor on the far left is also positive, which means that f of x is bigger than square root of 2. And that's all that was left to prove in our lemma. Now I'm going to need to reclaim this space here on my slide in order to finish proving the claim about the original sequence. I'll keep track of the lemma that we just proved. Now from our lemma, it's already clear that beyond the second term in our sequence, the remaining terms are decreasing, with square root of 2 as a lower bound. And this part is really by induction, where we use the lemma at each step of the induction. By the Monotone convergence theorem, our sequence converges to some limit L, which by the way is the infimum of the terms. not including the first term. Since square root of 2 is a lower bound for the terms, again not including the first term, the greatest lower bound is at least square root of 2. And now, let's remind ourselves that this is the formula giving each term of the sequence from the previous term. And in this formula, you can take the limit of both sides as n goes to infinity. On the left, simply the limit is L. On the right-hand side, now we need to use the formulas we worked out for working with limits, which we proved in the previous video. For example, on the right-hand side, you've got an an squared, so the limit of that is L squared. So the limit of an times an is just L times L. And then you can add 2. And then finally, since you're dividing by 2an, and the last thing we proved in the previous video is telling us the final limit is L squared plus 2 over 2L. That's a formula you can easily solve. You cross multiply and get L squared equals 2 after simplifying. Well, there's 2 roots of that, but remember that L is positive, so this gives L equals square root of 2. So that's a very natural way of constructing a sequence of rationals converging to square root of 2. Now, it's not the first example of such a sequence. Previously, we used the bisection method to give us another sequence of rationals, also converging to square root of 2. However, this sequence is nicer in several ways. In particular, this sequence is easier to compute. It's defined by simply iterating a very explicit rational function, f of x. Also, it converges to square root of 2 very fast. Now, if you want an approximation to square root of 2, that's correct, let's say to within 100 decimal places, then using the bisection method would require several hundred iterations by a much more complicated process than this. Here, we're iterating a rational function f, and only 8 iterations are required to get a rational approximation for square root of 2 that agrees with square root of 2 to within 100 decimal places of accuracy. So you just go to the 9th term, and you're already there. We say that the previous sequence, found by using bisection method, exhibits linear convergence, meaning that n iterations will give us an approximation where the number of significant digits of accuracy is roughly proportional to n. N iterations, n digits of accuracy. But here, the method shown has quadratic convergence, meaning n iterations give n squared, roughly, n squared digits of accuracy.